Welcome to the New Quantum Era. I'm your host, Sebastian Hassinger, and this is the podcast that features conversations with researchers working at building technologies that draw directly on quantum physics and quantum information science. On this episode, we'll hear another conversation I recorded at the American Physical Society's Summit. Thanks again to the APS for providing space and to Quantum Circuits for their help. My guest is Andrew Houck, a quantum physicist, a professor at Princeton University, and director of the Co-Design Center for Quantum Advantage, or C2QA. This is a national quantum initiative center funded by the Department of Energy and led by the Brookhaven National Lab with partners from academia and industry. The NQI centers have been really important forces for aggregating and focusing talent, resources, and innovation in the U.S., and at the APS Summit, a number of the center's leaders presented their progress and discussed their future plans. My previous conversation with Anna Grassalino was focused on her leadership of the SQMS Center, so I was really happy when Andrew agreed to also give us a perspective from the C2QA. So take a listen, and I hope you enjoy. So thanks for joining us, Andrew.
Thanks for having me.
Our pleasure. And I mean our, and I guess the royal sense. I often do this with a co-host, Kevin Rowney. He's not here this week. So, but yeah, thanks for joining me. So I saw your talk as part of the DOE NQI Center's sort of, status update yesterday, and I thought it was really interesting. In particular, you talked about this sort of trying to create a virtuous circle for increasing coherence time. So do you think that was sort of the central mission of the CTQA over the last 5 years?
Right. So the central mission is to sort of build the components you need to bring us past the NISQ era and into the era of fault-tolerant quantum computing. And that means bringing together people who work in materials and in devices and in software and in error correction and in architecture, because the problem needs to be tackled at all of those levels, and you need to make sure your gains at all of those levels are compatible.
Right. And so, I mean, there was the great story about tantalum. Were you surprised that was it was almost like incredibly low-hanging fruit? You described Kava, I think was the researcher who said, I explained how all these oxides are super different. Don't make devices out of niobium, right? I mean, that was kind of it was surprising how you sort of ran into that at the beginning of the center in a way.
That's right. I mean, some of these things are both low-hanging fruit and, or at least are low-hanging fruit in retrospect, but also are not easy, right? Other people have tried to make things out of tantalum. Other people have tried to follow the work in our papers. And one of the challenges in coherence and one of the lessons is that there's a quasi-infinite number of ways that you can mess up coherence. And if you're really only using one number, what's the lifetime of my qubit, what's the T2, and that's it. If you make a qubit with a new material, you might have messed up 4 other things, but made 3 of them better. And if that's all you look at, you'll never know. And so, we're using this playbook where we try and disentangle all of the different sources of loss. So you can see which ones get better, which ones get worse. And from that, you can actually start to build a much more comprehensive story as to how this works.
And what are the top sources of loss in your mind after sort of the last 5 years of sort of digging into this?
Right. So I should say all of this work is in collaboration with Natalie De Leon and Bob Cava at
an early guest on the podcast.
An early guest on the podcast. I know. I heard her guest a while ago, and so this is a status update, right? So we are working to improve many possible sources of loss. If you want to make a superconducting qubit, you have losses that often come from 2-level systems, sort of defects in some oxide, maybe some kind of impurity. We actually don't know, and this is a big grand challenge, what actually are the TLSs or the many different kinds of TLSs. But some of them live at surfaces, some of them live at interfaces. Tantalum has been really good at bringing down the surface loss compared to other metals.
Right.
In our previous generation of devices, we brought down the surface losses, and that made the bulk losses in the substrate actually the dominant thing. So by moving to high resistivity silicon now, we've knocked that down and have some of the very best performing qubits you can imagine. And now the questions are, what is left? Well, the surfaces still limit you, especially if you want to make small junctions. Interfaces matter. The actual Josephson junction itself is still made out of aluminum. That could be a problem both because of the aluminum oxide and because aluminum is a bit of a fragile metal. You can't sort of dunk it in anything. Tantalum got its name after the story of Tantalus in Greek mythology, who essentially embodies frustration. And it was named tantalum because the people who first started working with metal found it almost impossible to etch. And so it's incredibly chemically resistant. And that means that once you make something out of it, you can sort of put it in various acids. You can do a very aggressive cleaning steps, and that allows you to get rid of many of the residual hydrocarbons that could be causing loss. And so there's all of these kinds of things.
Whereas aluminum is much more.
Whereas aluminum, right? If we had our junctions on there and we did what we do to our tantalum, we would not have junctions left.
Interesting. And that's, I mean, so the CTQA, the acronym is Center for
There's two C's. Co-Design Center for Quantum Advantage.
And that was, the co-design was the part that I wanted to pick up on, because that even that description, as far down in sort of the whole stack of quantum computing as that is, there's basic material understanding, and then there's already design in the fact that you're bringing together materials in different to perform different functions. Is that sort of embody what you think of when you think of co-design?
So I actually think of two different things when I think of co-design. So there's sort of the more traditional way of thinking about co-design, which is moving vertically through the stack. So we make this materials work. We need to make sure whatever we do with materials can be implemented in a device, and that device can be implemented in some kind of cohesive architecture, right? Sometimes you can imagine a way to make a transmon with a really good coherence time that doesn't fit into what industry is doing in their scaled systems. And so the nice thing about the materials gains is they can often fit more readily into those systems. But then you do error correction on top of that. So one of the big wins in C2QA was some work out of Michel Deveray's group that showed that with these GKP states for error correction, you can get beyond break-even. It was one of the first experiments to show error correction beyond break-even. And in their first version of that, it was really hard because the transmon materials were the dominant sources of error. When they incorporated the materials gain, they were able to get beyond break-even. And then you can take these sort of bosonic error correction modes up the stack to think about how you build scaled systems. Can they be used to more efficiently do sort of near-term quantum algorithms? And by thinking of things all the way vertically through the stack, you can often get really important gains. One of my favorite ones from C2QA is this idea of using native bosonic modes. So some of the applications people might want to study in quantum computing are studying, say, field theories. Those have bosonic modes in them, and one of the costly steps is to turn those bosonic modes into a bunch of qubits. But if you actually have a resonator sitting on your chip, if there's something about your hardware, then you can natively use that to encode the bosonic modes and save maybe a factor of 1,000 in terms of the resource requirements. And this is really a co-design between the hardware and software levels of the stack.
Would that require sort of custom system architecture to be able to combine native bosonic operations with qubit operations?
So it would, though you could imagine something in between general purpose and custom where you're taking advantage of that. But frankly, we have in our best processors, 100, 200 qubits. We're at the point where we need to squeeze every last bit of computational power out of every element, right? We can afford to make custom circuits if they can do something particularly well.
Interesting.
There's another flavor of co-design that I want to talk about that I think is a little bit unique to C2QA, and also I think embodies what we try to do at the Princeton Quantum Initiative, which is another thing that I direct on campus. And that is what we call cross-platform co-design. So very often, and I think this is especially true for companies, but also fields in general, there's a bit of a monoculture, right? Almost every superconducting person at some point went through Yale, or at least went through somebody who went through Yale. And that's wonderful. It's because they've trained really excellent scientists, and they populate the companies, they populate most of the universities. But that means we all kind of think alike. We all learned the same lessons, and so when we tackle problems, we tackle them in the same way. very often, and frankly, in a modern era where everybody posts their papers in the archive, everybody sees everybody's result immediately, it's actually very hard to not think like everybody in your field, but the intersections with people outside of your field are harder to come by. And so some of the best ideas we have are taking ideas or approaches from one field and bringing them to another. So our work on tantalum, trying to figure out in a really robust way how to improve surface loss, followed what Natalie de Leon did in her postdoc, where she tried to improve the coherence of diamond NV centers as they got near surfaces for purpose of quantum sensing. It's almost the same problem. It's very different systems, but the approach works really well. You see this in other places, right? So Jeff Thompson and Shruti Puri at Yale and at Princeton worked on erasure conversion in these neutral atom quantum computing systems. And that turned out to be an incredibly powerful approach to making the most out of their elements. And that is what inspired the dual rail qubit, which also implements erasure conversion in superconducting qubits, which is, of course, what Rob Scholkoff is working on at Yale and at QCI. And so these ideas migrating from one physical system to another is what we call cross-platform co-design, because it really is helpful to get people who work on different systems talking and comparing approaches, problems, and solutions, because often the idea the problem has been solved in some other physical system.
Right. Yeah, actually, in conversation with Preskill the other day, he suggested that neutral atom platforms are almost a sandbox for experimenting with different approaches to error correction because you can reconfigure the qubit so plastically, right? I mean, there's no connectivity issues to worry about. You just use the tweezers to bring the right ones together.
I mean, that's certainly true. If what you wanted to have is 1,000 qubits that lasted a long time and had good enough gates that you could play with things in a reconfigurable way, that's definitely the playground you would want.
Right. That's so interesting. And when you think of cross-platform, when you think of the defining line between one field and another, is that down at the granularity of like different qubit modalities, or is it also different domains within physics? So maybe high energy physics or astrophysics or other domains as well.
So it really goes at different levels of the stack. It goes in different ways. So at the materials and device level, I think about it as qubit modalities. Right. At the higher levels of the stack in applications, I think it's getting domain experts talking to quantum computer scientists and talking to quantum computing experts. And so, one of the things we saw in C2QA was an enormous gain in efficiency for simulating nuclear physics problems that came from Nathan Wiebe talking very closely with a bunch of nuclear theorists and learning about sort of how to use domain-specific knowledge to develop sort of more interesting algorithms. And so it's really about bringing people together. And frankly, this is one of the big challenges in science, right? I think of quantum information as this big 3D grid where you have sort of all the qubit modalities sort of horizontally next to each other, and then you have this vertical stack that's sort of materials, devices, architecture, error correction applications. And then, of course, there's experiment and theory in all of those levels of the stack. And it's, everybody sort of occupies a point or maybe an area in that. And when you build an institution like C2QA or like the Princeton Quantum Initiative, the goal is to try and populate that space. But you have to populate it with people who see the value in trying to bridge those connections, because otherwise you have sort of, a very sparse matrix with almost no connectivity. And so the kinds of things we're trying to build are really special collaborations. And we're looking for people who see the value in talking to people outside of their comfort zones and really trying to sort of enjoy science expansively.
Science and also, I mean, to me, that's the smartest approach for trying to answer the question of what are the applications of these devices. If I keep thinking about Stan Ulam at Princeton IAS coming up with the Monte Carlo approach to, I think, neutron diffusion calculations or something in the late 40s, early 50s, and then like 25 years later, somebody's saying, this would work on financial portfolios. Like the scientific techniques to use these devices in the way that Feynman described, to simulate many body systems, is likely. I mean, it's scratching an immediate itch that you can satisfy with something we can build today or in 2, 3, 4, 5 years. which may indirectly lead to sort of broader applications. Those techniques are effective, and then it's a search for like, what else can you do with these techniques?
Yeah, that's exactly right. And it's always, people are always asking me like, what's going to be the first application of quantum computers? And it's always a hard question because there's only a very small handful of problems where you can prove in an end-to-end way that you can show in an end-to-end way that in all situations our best quantum algorithm is definitely better by a huge margin than our best classical algorithm. No proofs in that space, but at least we have a known algorithm that we can prove a runtime on a quantum computer. There are also a whole bunch of heuristics where it's like, maybe a quantum computer will work on that. We don't really know if it'll be better, but let's try it out. And until we have the hardware, you can't try it out. And so, I expect there to be surprises. But I don't know what they are because they're surprises.
They're surprises. It's the C2QA for surprises. So you are, the DOE is in the process of sort of, getting the centers to resubmit proposals. Are there any sort of course corrections or major new elements to what you're planning for the next 5 years?
Definitely. I think it would be, in a fast-moving field like quantum information, you can't imagine that 5 years go by and you're like, we got it right exactly 5 years ago, 90 PIs, spread across 25 institutions, and we're going to stick exactly with what we have. We are planning to bring in some of the really exciting developments. So we are bringing in a lot of the work on neutral atom quantum computing. Many people in our center were part of those developments, right? Jeff Thompson's work in neutral atom quantum computing. And that means we're sort of ramping down some of our efforts in quantum networking. We had some erbium-based quantum networking work that was really exciting and it made incredible progress. But it feels like the neutral atom work is more of a priority. There's been an enormous growth an enormous effort that arose in diamond growth at the Princeton Plasma Physics Lab, thinking about bulk diamond growth for quantum sensing purposes. And that feels like it's important to bring in because the kinds of problems, again, that you tackle in diamonds are the same as the kind of problems that you tackle in superconducting computing materials. And so we're going to have sort of one effort that's really focused on materials, broadly writ, and how you can build up this field of material science for quantum information, and another that's thinking about quantum computing in the vertical stacked direction, especially on problems around modular quantum computing. So most physical systems are going to run into some kind of wall. Neutral atoms are going to run out of laser power when they hit a couple thousand atoms. Superconductors are going to run out of chip size, at least, and so you have to figure out how to go off chip. Ion traps, there's only so many ions you can put in a trap before the Coulomb forces sort of make things get a bit awkward. And so we're getting to the era where everybody's quantum computer is getting past the point where it's comfortable in a module. And so then the question becomes, what's the ideal module size? How many qubits do you want? What connectivity do you want? What kind of connectivity between modules do you need? What kind of fidelity? What kind of rates? How do you sort of take algorithms and error correction and compile them to those modular systems? And that's a very large co-design challenge because you might have an idea of an algorithm you want to do. You might have an idea of some error correction you want to run. You might have some devices and some actual figures of merit for your modules and for your interconnects. And now how do you put all those together and what's the missing piece that you could invent on the sort of device side that would make the architecture flow much better? Those involve resource estimates, sort of computer scientists, computer architects, material people, device people, all working together. And you just can't do that kind of thing outside of a center.
Right. Yeah, I think you mentioned sort of the potential for very complex connectivity sort of topographies, right? Where there might be nearest neighbor and then one far neighbor as an example, sort of. And I can imagine extremely complex graphs that are sort of designed to solve a particular algorithmic problem. That's sort of what you're...
That's the kind of thing, right? Yeah. So for instance, in neutral atom quantum computing, you have a high degree of reconfigurability within a module, but nobody has yet demonstrated module-to-module links between neutral atom systems. In superconductors, it's very natural to make nearest neighbor coupling, but some of the error-correcting papers on LDPC code show if you can get a little bit of longer range coupling, then that's a lot better. But also, how do you couple from one chip to another chip, right? You probably don't want to go from fridge to fridge, but from chip to chip. Do you just use a wire? Do you use a cavity? How do you build those kind of couplers? So there's an enormous number of questions on the hardware side, and then what does that mean for error correction, right? What does that mean for algorithms, and how do you sort of mesh this chopped up grid of small processors that are connected probably with worse links than you have just from neighboring qubits? How do you do that sort of chopping up and division in a way that is efficient?
I'm glad you're thinking that far ahead, because it'll be great when we get the those sort of optimal modules, as you put it, of function. But you're right. I mean, when I start looking at the way the architectures are evolving, it does feel like they're going to top out at some point before they're really achieving the kind of scale we want. It's very hard to imagine a million superconducting qubits in one fridge on one chip. Right?
Well, I mean, one fridge, maybe one chip. I think is harder. But if you imagine it on one chip, right? The reason you have to think about it now is that you don't want to then build up your single module to be a universal quantum computer that can solve any NISQ problem. Or maybe you do, but that might back you into a corner where going beyond that module size isn't actually the right path. And so you sort of need to think like, okay, I'm going to make some decisions that are going to make the best NISQ-era quantum computer I can make on a single chip. But I'm going to recognize that once I go past that, maybe what I want on one chip isn't a general purpose NISQ-era quantum computer. It's a machine that's optimized to do X. And that thing can be connected to other similar modules, and all of the interesting computation comes in the connectivity layer and not in the module itself.
I see.
And so you have to sort of think about those architectures and those problems you want to solve in order to design the modules and to design the physical systems. And so you can't just say, well, when we get to that problem, we'll figure it out, because you might have spent many years of effort going not quite the right way you want to go.
Right. And you mentioned the Princeton Quantum Institute. How do you manage sort of the collaboration? What's the advantage of having those two sort of entities? I mean, one's obviously Princeton specific, and the other is multi-institutional and also private and public. How do you manage that collaboration between the two?
So I mean, they're sort of very different entities, right? So as one of the co-directors of the Princeton Quantum Initiative, our goal is to build up quantum information science on campus. Princeton doesn't think just in terms of what are we going to do for the next 5 years. We are making one of the largest investments we have ever made in any field by building up a building for quantum information science, by bringing new people to campus. You don't make that kind of investment for 5 years. That's a 50, 100-year investment, that this is something that we think will be important. As we build that up, we are trying to bring people to campus who will collaborate and will work together, and who see the value in coming together in a new discipline that brings together people with different disciplinary trainings. C2QA is more aimed at tackling the kinds of challenges that are needed immediately to bring us forward as a nation, right? It's part of the National Quantum Initiative. It's a national effort to make sure that we keep our lead in quantum information science. And it's built on an idea that this three-legged stool of collaboration can solve problems that you can't solve just at a university or just at a company or just at a national lab, right? Universities are really good at innovating new ideas and at trying them very quickly. Most of the new ideas in quantum information science still come from universities and find their way into companies. Companies can build things at scale that you just can't build at the size of a single PI in a university, especially when your graduate students, keep leaving and you have to keep training new people. And national labs have this enormous investment in infrastructure and talent, especially around very specific problems. So in C2QA, we leverage investments in material science. There's the beamlines, the light sources, the Center for Functional Nanomaterials that have incredible expertise at material science and these billion-dollar tools for doing material science that had not really been applied to problems in quantum information, and an enormous amount of expertise in co-design and in advanced scientific commuting. And trying to apply that expertise and that infrastructure to problems in quantum information is incredibly important. And so C2QA, I feel like, is focused on bringing together academic talent spread around the country, industry, and leveraging national lab investment. Whereas Princeton is trying to build something that is much longer lived and really builds a completely internal talent pipeline of people who want to collaborate up and down the stack and horizontally around the stack and between experiment and theory.
Excellent. And Princeton's investment at that scale in quantum information, is that because of a belief in sort of the practical applications of quantum computing, or is there a belief that quantum information is sort of the next foundational advancement for quantum mechanics and physical sciences generally, or both?
Yes. It's both.
I realized as I was asking that question, it's clearly both.
You want to make an investment in something that you think is going to have an impact on the world, right? That's one of Princeton's mottos, is Princeton in the service of humanity. We want to have an impact. We also care about deep foundational questions on the nature of the universe. And quantum information brings together both of these things, right? That's why I was attracted to this field 25 years ago. I switched between physics and electrical engineering as my undergraduate major enough times that I think everybody was incredibly annoyed with me. But I had this sort of this yearning to study deep and interesting questions about the universe, but also do useful things. And this allows both of those to go together.
It is the 100th year anniversary of quantum mechanics. Would you hazard a guess to what the next 100 years will bring in terms of the science?
Well, I mean, 100-year guesses are always better when somebody isn't recording.
The record will be long gone.
That's what they always say when they trap you into saying something dumb. I think one of the things that's really exciting about quantum information is we are building systems that are becoming macroscopically large, right? A million qubit quantum computer is basically a cat. I mean, it's like less fuzzy and cute, but it's essentially Schrödinger's cat. And as you build these systems up, you can start to really ask questions about, do we actually understand quantum mechanics? Do we understand quantum mechanics as it turns into these macroscopically large objects? Is there something else lurking there? Can we really understand this sort of interface between classical and quantum?
That's really interesting. Excellent. Well, that was a fantastic conversation, a great overview of the C2QA. I'm looking forward to what you guys do in the next 5 years.
I'm looking forward to it too.
Very impressive. So thank you very much.
Thank you so much for having me.
Thank you for listening to another episode of the podcast, a production of the New Quantum Era, hosted by me, Sebastian Hassinger, with theme music by OCH. You can find past episodes on www.newquantumera.com or on Blue Sky at newquantumera.com. If you enjoy the podcast, please subscribe and tell your quantum curious friends to give it a listen.